So, hello everyone, my name is Mark Hoffmann from Data and Motion Consulting, and today I want to give you some insights into the new OSGi messaging specification that is currently work in progress and will come with the next specification release. But at first I want to introduce myself and my company. I am the CTO of Data and Motion Consulting. Our company is located in Jena, Thuringia, the so-called green heart of Germany. And our working areas beside OSGi and modular software are distributed environments and as well model-driven software development. We do a lot of trainings in that areas as well. So yeah, that's it. We are an active member of the OSGi Alliance and are currently involved in some specifications, in my case, the messaging specification. So now let's see which topics we want to cover in the talk. At first, I want to introduce you into the new messaging specification and give you a brief history about messaging in OSGi. And after that, we will go and dive into some technical stuff, and you will see how to publish a message or how to subscribe messages. And after that, we will take a look at some optional features, for instance, the reply-to behavior, which is a complex topic, and acknowledgement of messages. So, but for now, I want to turn off the webcam view to not cover up the slides. Okay, let's begin. So, in today's world, event-driven and asynchronous communication is becoming more and more important. And especially in the IoT area, there we want to have some sensor data published from a sensor instead of periodically pulling them. And asynchronous communication can help with that. There are a lot of protocols in the white, also standards like MQTT, AMQP, JMS or Kafka. Some of these protocols are standardized, and there are maybe a few implementations from different vendors for that. And beside these asynchronous behavior itself, also the handling of these events or messages became an essential part in software development, and many frameworks for reactive streams arose in the past years. And also OSGi has a specification for handling reactive streams, the PushStreams specification. So, in messaging, we heavily use these push streams. In general, in OSGi, asynchronous messaging already has a history. We have the event admin specification that provides an own event mechanism, but this only works within an OSGi framework and is not able to communicate to third-party systems. There have already been some RFCs for distributed eventing or the MQTT adapter that never really became a specification for certain reasons. So some years ago, we at Data and Motion started a project called Gecko Messaging that had the goal to have one API with different protocol implementation, in our case AMQP, WebSockets, CAN, and MQTT. I already gave a talk a few years ago about that in PushStreams and showed how different implementations and PushStreams can be used in a practical part. And out of this, the RFP and now the RFC and the specification came out, and now I'm happy that messaging will become a specification. So the messaging specification itself is no implementation. It is more a common API or infrastructure that covers common messaging patterns or use cases. So we're not intended to implement or apply high sophisticated enterprise messaging features like in products of MQ series or TIBCO EMS. We think it's not possible to bring all these products under one umbrella, one API. That's why we just concentrate on certain cases and patterns. And in addition to that, the specification will make several implementations, or can make several implementations for asynchronous communication systems OSGi compatible, so that users can take profit from services, configurations, and so on. The specification will also contain the possibility to introspect the implementation using DTOs that you can see if connection errors occurred or whatever is the state of your client. Because there's a wide variety of existing products, there's also a wide variety of features. So the specification supports several optional functionalities and as well possibilities to extend the base functions to enable vendors to provide their own additional proprietary features. So our main goal is to handle different protocols, messaging protocols and implementations in a similar manner. So when we take a look at the example in the slide, we can see that the implementations for certain protocols are quite different. And it's just for publishing in the Hello World via MQTT, AMQP and XMPP. But some stuff is very similar, like providing connection information, connecting itself. So if users are in the situation where they have to deal with different frameworks, that means that they usually have to learn a new API or a different API. And the messaging specification tries to hide that implementation or vendor-specific semantic behind an API and a service-based infrastructure. So with an implementation of the messaging specification, the example from before could look like this. You could get message publishers injected, the targets bindings at the reference annotation bind the wanted protocol to the corresponding instance. So we see a protocol specific and vendor agnostic injection. So by just extending the target filter, this would allow you to be more specific about the service you want. In addition to that, we have a builder factory. The message context builders are a way to conveniently create messages. And as you can see, this publishing of the 3 different messages for 3 different protocols can be done with the same API. And the declarative services from OSGi can take care of providing functionality to select the right service implementation. And the message publisher interface is straightforward. It has the publish method. It accepts a message to be sent. We use the message context builder to create messages in a fluent way. In that example, we use the builder to provide channel information and the message content. Subscribing to a message is very similar. The message subscription service is injected into your service component, and with a message context builder, you can configure your subscription. At a minimum, you want to provide the channel information on the channel you want to subscribe on. This messaging subscription interface is also straightforward. It has a method that accepts the message context, which is a subscription configuration, and returns a push stream of messages. Each message that arrives on the configured channel will then be published in the push stream. An implementation has to take care of the correct handling in case of a connection loss. If a user, on the other hand, closes the push stream, the implementation has to close the event source and to unsubscribe from the channel if necessary. So now we want to take a look what's the difference between messages and message context. A message is a simple wrapper that represents the content that wants to be sent. We use a byte representation that enables us sending all kinds of content. In addition to the content itself, the message contains a message context. This is comparable to message headers or properties. In this case, the message context is more typed and contains meta information about the message. It holds information such as content encoding, content type, correlation ID. Also, additional headers can be put into an extension map. This allows users to place vendor-specific data to the context, and with that, this can be forwarded to an implementation. So usually, if a user publishes a message, these context information can be provided using the message context builder. So they are provided by the user. When you subscribe on a channel, then the message context is created by the implementation based on the event or message properties from the underlying implementation. So the messaging specification says that implementation must always provide at least the message publisher and message subscription service and their corresponding message context builders. This is the minimum of functionality that must be provided via the messaging specification. But as mentioned before, we also have optional functionalities. One of that is the reply-to behavior. This is an RPC-like pattern where you send a request message and get a response message back. This whole procedure is then asynchronous and non-blocking and follows the request response pattern. In our case, we found two sides of the reply-to behavior. One use case is simply the reply-to publishing. This covers the sender side where you send a request and expect a response. The second use case is the receiver side where you receive a request and have to handle and build a response message. In the specification, this is realized using a Reply-To-Whiteboard that executes subscription handler services. And now we want to take a closer look at these two features. At first, a reply-to publishing means we send a request message and get at least one response message back. For that, we also use a service that is provided by the implementation. The service interface is a reply-to publisher. It contains the method publish and reply that accepts a request message and returns a promise for a response message that resolves as soon as the message arrives. Usually the request message must contain additional attributes like a correlation ID. This ID is then also set to the response message properties so that when you receive a response that you can assign a request and response to each other. Some protocol implementations support the automatic generation of these IDs out of the box. And in case that an implementation supports that, it must announce that using common service properties. And usually beside the correlation ID, the request message also may contain a reply-to channel information. This means that then a response will be sent back over that second reply-to channel. This is a common pattern because in this behavior we talk about an exclusive connections. And many protocols also support the generation of a reply-to channel. So this is also a feature that can be announced from implementation. An implementation itself has then to take care of unsubscribing from that exclusive response channel after the response message has been received. So on the receiver side, the behavior is quite different. Implementation must provide a whiteboard, in our case the reply-to whiteboard, and user code can then be implemented into so-called reply-to subscription handlers. We know 3 interfaces. One can handle a request message without creating a response. This is for send and forget handling. The second accepts a request message and returns a response message. And the third interface accepts a request message and returns a push stream of response messages. So the user can easily implement its business logic and register the implementation as a service using one of these 3 interfaces, these subscription handler interfaces. And in addition to that, you need some service properties to bind the service against a certain reply-to whiteboard instance, and a second one to give information about the request channel you want to subscribe to. So if a request message arrives on the defined request channel, it is accepted by the whiteboard, and the whiteboard then delegates the request messages to the corresponding subscription handler that was injected into the whiteboard instance. The setting of correlation IDs to the response message builder in that case, and also publishing the response message that is created from the subscription handler to a correct reply-to channel are tasks of the whiteboard implementation. So a user doesn't have concern about that. So as mentioned before, the reply-to behavior is completely optional, but any implementation that supports this feature must also support the publishing and the subscription side. So, and reply-to behavior is also announced using service properties and the corresponding services itself, and also properties in the service runtime DTO. So the next part of our optional features is acknowledgement of messages. Messages can be explicitly accepted or rejected, where rejection is quite different to simply not acknowledging a message. A rejection can mean a redelivery of a message in a messaging system. So this is usually a protocol or implementation specific. So we know variants of handling acknowledgement. We have a direct acknowledgement. That means that messages will be acknowledged or rejected using filters or callback before they enter a push stream. And on the other hand, we have programmatic acknowledgement, where you have the possibility to handle that actions during the processing of the messages in a push stream. Acknowledgement itself has an own API, so that knows an own specific message context builder as well as an acknowledge message context, and also an acknowledge handler that is used to trigger acknowledging or rejection by hand. So if an implementation supports acknowledgement, it must also provide implementation of this API. For a direct acknowledgement, the user uses this specific API, like an example. This includes the acknowledge message context builder. The example shows how you can retrieve that over the message context factory service. And this special builder has additional methods to provide callbacks that configure the acknowledgement. You can use Lambda expressions for that. We have the possibility to filter messages using predicates. We have the possibility to handle the acknowledgement using a consumer. And we also support a post acknowledgement, which is executed after the acknowledgement or rejection happened. So you can either use the Lambda expressions for the configuration, or there's also a service-based variant that can be used. All these methods have counterparts that accept a string with an LDAP style target filter, and with these expressions in implementation looks for corresponding services in the service registry that match that LDAP filter style and the corresponding predicate or consumer interface. And then these service instances are used for filtering acknowledgement or post acknowledgement. So to trigger an acknowledgement itself, you will need the acknowledge handler, and you can retrieve that from each message using the message context, because implementations that support acknowledgement must implement the acknowledgement API. Means that all messages that you get will then have a message context, which can be casted to acknowledge message context that provides you with an acknowledge handler instance. And with that, you can then trigger acknowledgement or rejection. The programmatic way of acknowledgement uses the same style in general, but this can happen inside a push stream. So as long as an implementation support acknowledgement and you still have a message instance in your hand, you're able to cast a message context to the acknowledge message context and get the acknowledge handler. So you are then free to decide at which state in the push stream you want to acknowledge or reject the message. So that's it. I think we covered powerful features in the specification. That I hope this will help to ease the use of various messaging protocols. So currently the state is that the RFC 246 was informally accepted, and at the moment we have already started writing the specification. The API is not final now. It may change during the implementation. After writing the specification, and reference implementation will follow, as well as the compliance tests. And it looks like that we use MQTT as protocol for our reference implementation. So that's all. Thank you very much for joining my talk, and have a nice time. So I hope everybody can hear me. We have a question. Is there currently a working example implementation on that we can try? And if so, what message brokers are currently supported or plan to be supported in the future? So in the end, this is just a specification, and everybody can create its own implementation for any protocols they like. We currently have no implementation. There will be a reference implementation during the specification phase. And at this point, we plan to implement MQTT as a protocol. But the specification came from an old project which is available, which is also open source. It's available on GitLab. It's called gecko.io, and it's called Gecko Messaging. If you're interested, just contact me over this web card, and you can get the link for that. And we have already an implementation that nearly supports all the features of the messaging specifications. We have currently support for MQTT and for AMQP, WebSockets, CAN bus, and we have also some guys that are interested for an implementation for Kafka. So that's it. So are there any further questions? Another question is there any time plan for a reference implementation? Currently, we are planning to create the specification first. So at first, the specification writing comes, and after that, we will start with the reference implementation. Yeah, we hope to get that in work for next year, the first quarter next year. So currently, I think the writing process will take some time now until December, and then we can start with the reference implementation. So further questions? So if someone wants to get in contact with me, just contact me over Swap card or write me an email. The contacts are in the presentation, so feel free. Okay, then, bye.